Hello students, this lesson is on the law of sines, which will give us a tool for finding side lengths and angles of non-right triangles. First, some terminology. An acute triangle is a triangle where all three interior angles are acute, meaning that they are all between 0 and 90 degrees. An obtuse triangle is a triangle where one and only one of the interior angles is obtuse, which in this drawing would be the theta, meaning that it's an angle that's more than 90 degrees, but still less than 180. The other two angles will have to be acute. An equilateral triangle is a triangle where all the interior angles are equal. Furthermore, they are all 60 degrees. Furthermore, the side lengths, the side opposite alpha I'll call side length A, opposite beta will be B, and opposite theta we'll say is C. And all of these side lengths must be the same. You might remember this notation. You put a single hash mark through each of these angle notations. That suggests that they're all equal. And since I've already used a single hash mark, if I put a double hash mark through all the sides, that suggests that they are equal. Now, an isosceles triangle, two of the interior angles, we'll call them alpha and beta, must be equal. The other angle may or may not be different. If theta is equal to alpha and beta, then we're looking at an equilateral triangle again. But if we're looking at an isosceles triangle that's not equilateral, then theta would need to be different from alpha and beta. Again, the side opposite alpha I'll call A, side opposite beta will be B, and side opposite theta we'll call C. I'll maintain that consistency throughout this lesson. And side lengths A and B must be the same. So alpha and beta have the same measurement, and the lengths A and B have the same measurement. And then a scalene triangle is a triangle where the three sides are all different length. And the interior angles, none of these are the same either. Now we're going to work with a lot of scalene triangles in this lesson. So here I've drawn an arbitrary triangle, and it appears to be an acute triangle, but I could have also drawn it to be obtuse. So think of this as general, not necessarily to scale, and it represents both acute and obtuse triangles. One thing to remember about all of these angles is that the sum of the interior angles must always add to 180 degrees, or if you're in radians, pi radians. Also, the sum of any two sides must always be more than the third side. So length A plus length B must exceed length C. Length A plus length C must exceed length B, and length B plus length C must exceed length A. And then one more thing to state, something known as the law of sines. It states that if you take any side length, such as side length A, and divide it by the sine of the opposite angle, so that would be the sine of alpha, this will be equal to the same ratio of any other side opposite angle pairing. So this will equal the length B divided by the sine of beta, and will be equal to the length C divided by the sine theta. Furthermore, you can invert all of these and write it this way. This lesson will focus on using the law of sines to help find missing side and angle measurements of non-right triangles. Okay, let's go to the next page. On this page, we discuss the solvability of SAA triangles. Now, an SAA, which is known as a side angle triangle, is one where any two angles and any one side are given. The side could be opposite one of the angles or be the side that's between the two given angles. Below are three SAA triangles, because in each case, two angles are given and one side. Furthermore, the side that's given is opposite one of the given angles in this first case. This middle case, we have two angles and one side. This time the side is not opposite either of the given angles, it's in between them. And here's another case where we have two angles and one side, and again, this side is opposite one of the two given angles. Now these triangles are not necessarily drawn to scale. We are going to determine whether each triangle is solvable. If so, classify the triangle as acute or obtuse, then solve the triangle, and what we mean by that is find all missing sides and angles. Okay, so we do have a missing angle here. Let's call this alpha. Its opposite side is also missing. We'll call that A. I always will use A opposite alpha. We can call this 80 degrees beta, and opposite it will be B. That means 40 degrees we're saying is theta, and we're saying C is this 10 meters. Now the first thing I recommend finding is alpha. Whenever two interior angles of a triangle are known, we can always find the third angle, because they must always add to 180 degrees. So I just have to solve this for alpha, and we get alpha has to be 60 degrees. So now I know all of the interior angles. It remains now to find the two missing side lengths. This is where we get to use the law of sines. Let's focus on finding side length A first. We know that A divided by the sine of its opposite angle will be equal to any other side divided by the sine of its opposite angle. Now, I could say that this will be equal to B divided by sine beta, but this will not be very helpful setup because I don't know A and I don't know B, so there are two unknowns in my setup. But I do know alpha and I do know beta. So instead of using the B over sine beta, let's use the C over sine theta, because here I know C, I know theta, and I know alpha. So I know 3 of these unknowns, and I can solve this for A. I'm going to begin by multiplying sine alpha to this side. We know C is 10 meters, alpha we determined was 60 degrees, and theta is 40 degrees. So this is as much as we can simplify without a calculator. Using a calculator and making sure it's in degree mode, we get about 13.47, and this will be measured in meters. Now I can find the value of B in the same way. We know that B divided by sine beta will be equal to, and since I've just figured out what A is, I could use A over sine alpha and then solve this equation for B, but then you might be tempted to use this rounded version for A, which would introduce some error in the calculation. So this would be the best expression you would want to substitute in for this value of A. And if we want to avoid that complexity, let's use the ratio of C over sine theta, because C is a whole number 10. So again, we're going to multiply the sine beta to this side, giving me C times sine beta, and then all over sine theta. We know C is 10, we know beta is 80 degrees, and theta is 40 degrees. And this gives us about 15.32 meters. Now be careful that you are not tempted to look at this drawing and deduce whether or not these measurements make sense, because this drawing of the triangle is not necessarily to scale. It's just a general reference triangle that's being made. All right, this next one, let's say B is the given 8 centimeters, so beta is the opposite angle. That's the one we don't know yet. We'll say theta is just 30 degrees, so length C is opposite that. And this 40 degrees is alpha, and we'll say side length A is opposite that. We can find beta right away. Beta has to be 180 degrees minus alpha minus theta. Oh, and I should have mentioned on the last triangle that we were supposed to classify it as acute or obtuse. So in this first triangle, all the interior angles turned out to be acute. So we had an acute triangle. That won't be the case for this next one, because it turns out that beta is equal to 110 degrees. So already I know that we have an obtuse triangle. Now, in our picture, it does not look like beta is obtuse, but again, this picture is not necessarily to scale. Now I want to find A and C. Let's begin with A. We know that A divided by sine alpha will be equal to, let's use the B beta ratio because both B and beta are now known. So A is equal to B times sine alpha divided by sine beta. B is 8, alpha is 40 degrees, and beta we just found is 110 degrees. This gives alpha is about 5.47, and this time our unit of measure is centimeters. Now let's find C. C divided by sine theta must be equal to the ratio of B divided by sine beta using the law of sines. Therefore, C is equal to B sine theta divided by sine beta. B is 8, theta is 30 degrees, beta is 110 degrees, and we get about 4.26 centimeters in this case. Let's go ahead and circle our answers. And let's take a look now at our third. Let's call this missing angle theta, but notice what the other two angles already add to. They add to 200 degrees, but the sum of the interior angles must be equal to 180 degrees, and so we have an impossibility here. Now, in our drawing, we did draw a triangle, but in reality, if one angle is 70 degrees and the other is 130 degrees, then it will not be possible for these two sides to meet up. Apart from this issue, if the two given angles in an SAA triangle add to less than 180 degrees, then we will always be able to find the third angle. Furthermore, the triangle will always be solvable. And they are only unsolvable when the two given angles add to 180 degrees or more. Okay, let's go to the next page. This page explores the solvability of SSA triangles. Now, an SSA, or side-side angle triangle, is one where two consecutive sides, A and B, and the angle opposite one of those sides are given. Without loss of generality, we can say that the angle that is given is the one that's opposite A, which we're calling angle alpha. So in such a triangle, we know one side, another side, and we know an angle that's opposite one of the given sides. If such a triangle is possible, then we can simply use the law of sines to find the missing angles and sides. But let's first determine conditions on the length of A, which will determine whether one, none, or more than one triangle are possible. To help understand this, Look at this picture where alpha we're going to fix at 50 degrees, B we will fix at 5 units, and A we will fix at 3 units. And now I'm going to vary beta. And you can see that no matter what angle of beta I choose, it's impossible for the side A to reach the horizontal leg. So this would be an example of an impossible scenario. What if I lengthen A? Now as I vary beta, you can see that we will be able to close off the triangle somewhere around this measurement, 90 degrees, but maybe not exactly 90 degrees. Notice if I zoom in, I don't have a perfect connection here. So this triangle would be possible, and I'd have to find some beta that's near 90 degrees. What if A is a little bit shorter? Let's make A a little bit shorter than B, so 4.8 compared to B being 5 units long. And now when I rotate beta, I can see I'm going to get one answer right around here, so around 77 degrees. But if I keep rotating, we will get intersection with the horizontal line segment once again around 3 degrees for beta, creating a very skinny triangle. But there are two solutions. Make A a little bit shorter, I can see a solution here, and then another solution roughly here. Make A too short, and I get no triangle is possible. So the first thing we want to do is figure out how long A would have to be so that I was able to reach the horizontal line segment only by becoming perpendicular to it. In other words, making a right triangle. Okay, in this case, let's figure out what the length of A would need to be to make this perfect right triangle. So we know that the sine of alpha, which is opposite over hypotenuse, would be A over B. Therefore, A would have to be equal to B times the sine of alpha. If A is this perfect length, then we can only make one triangle. So if A is this perfect length, then I will only be able to make one triangle, and that happens precisely when we make a right triangle. So beta would have to be 40 degrees, complementary with the 50 degrees that is alpha. If A is any shorter than that perfect amount, then we'll have no triangle possible. Let's see now what happens when A is more than this amount. And let's grow A to a length that matches B. If A and B have the same length, and then I rotate this direction, you'll see that there will be no triangle possible as we move this direction with beta, because we will only hit the horizontal line when there is no triangle left, when beta is 0. But if you rotate this direction, we will get one point of intersection somewhere over here. Now if A goes longer than B, we will have a similar issue. Rotating beta to 0 won't allow us to complete a triangle, so we will only have the choice of rotating out this way until we intersect the horizontal line again. So if A is B or more, then only one triangle is possible. And it won't necessarily be a right triangle. Unlike up here when A is this perfect length, then the one triangle that's possible would have to be that right triangle. So if we explore our different values of A on a number line, we don't want A to be any less than 0. Here's when we take on the value B sine alpha. B will have to be more than that because alpha is acute and sine of alpha therefore is less than 1. We see what happens when A is B sine alpha. We get one right triangle. We see over here that if A is less than this, then no triangle is possible. If A is B or more, then only one triangle is possible, which leaves a gap between B sine alpha and B. This gap right here will be the values of A for which two triangles are possible. So we need to shrink A to be less than 5, but still be more than the perfect size that gives us the right triangle. And so here we'll park A at 4.2, and if I change my angle beta, notice I get one triangle right around here, and keep rotating, and we get a second possible triangle right around here. So in summary, if A is a value somewhere in the interval from 0 inclusive up to B sine alpha exclusive, then we have no triangle. If A is B sine alpha, we have one triangle. If A is somewhere in the interval from B sine alpha up to B, excluding both endpoints, we get two triangles. And finally, if A is B or more, in theory up to infinity, we go back down to just one triangle possible. Let's use this information on the next few slides. Next page. The triangle below is not drawn to scale. Determine whether it is solvable. If so, solve it and then classify the triangle as acute or obtuse. So here's our work from before. We're calling 40 degrees alpha. This 10 feet is our value of A, and this 6 feet is our value of B. First thing I want to do is find this crucial cutoff value. So B times sine alpha will be equal to 6 times the sine of 40 degrees, which is about 3.8567. I'll go a little more precise with this. So I could now completely adapt my windows here to this problem. I can adjust my cases to this. And now we simply have to ask ourselves, which case does 10 feet belong in? and that would be our bottom case, telling us there will be a triangle and only one possible answer here. With technology, we can see that A was certainly long enough to prevent a triangle being drawn over this direction, but as beta increases, we will eventually get to a point where we can make a triangle, and we expect an answer of around 117 degrees. So let's label some of the missing angles and sides. The angle opposite B we'll say is beta, the other angle will be theta, and the side opposite that we'll say is C. Since I know information from this pairing, this will be one of my ratios I use in my law of sines, and I know half of the information from this pairing. So let's find the other half. And this time I'm looking for beta, so I'm going to write my law of sines this way, that the sine of beta divided by the length b, so I'm doing the sine in the numerator and the side length in the denominator this time, this will be equal to the sine of alpha divided by a. Furthermore, I know that since we had to swing this side past vertical, I know that this angle here will be acute. So let's solve for beta. We have sine beta is equal to b sine alpha over a. Therefore, beta will be equal to the arc sine of b sine alpha over a. This argument will be a positive argument, giving us a first quadrant angle when I do arc sine, which is exactly what I'm looking for because we know that beta must be acute. Specifically, we get that beta must be the arc sine of 6 sine 40 degrees over 10. Reach for a calculator and make sure you are in degree mode for all of this. In Desmos, you can just type in the word beta, and it makes the beta symbol. And we said beta was equal to the arc sine of 6 sine 40 degrees over 10. Click the wrench and make sure you are in degree mode, and this gives us our beta value. And we get beta is approximately 22.69 degrees. So now I know alpha and beta, so I can find theta by doing 180 degrees minus alpha minus beta. So the question will be, should I use this rounded version of beta in my calculation, or should I use this more precise notation? Well, if doing this with technology, I recommend you do the following. So to find theta, we just have to do 180 minus alpha, which was 40 degrees, minus, and then instead of putting in a rounded number here, just enter the symbol beta or type in the word beta, and I get a more precise number. So this idea of storing complicated numbers as variables and then using those variables in a separate calculation allows you to maintain your precision. Well, right here we can see that this is obtuse. So this triangle is an obtuse triangle. And lastly, I need to find the length c. So since I'm looking for c, I'll put that in the numerator. And using the law of sines, we divide it by sine of theta. And this should be equal to either a over sine alpha, or I can use b over sine beta. But I'm going to use the a and alpha combination because those numbers are easier. So this gives me that c is equal to a sine theta divided by sine alpha. Now again, to maintain precision, instead of using this rounded decimal for theta, I'm going to store the value theta in my calculator, and then we will do a 10 feet times the sine of theta divided by the sine of 40 degrees. You can store this value by typing in theta. This gives us an error. Turns out theta is a protected variable in Desmos. We can use some other letter instead, perhaps a capital T to stand for theta. And now I want to calculate c by doing 10 feet times the sine of theta and dividing this by the sine of 40 degrees. This maintains my precision, and we get about 13.82. And this would be measured in feet. All right, the next page. Same instructions. In fact, notice that we have the same value for b and alpha. So the question will be whether this new value for a is long enough to make a triangle, what kind of triangle, and how many triangles might be possible. But because we have the same b and alpha, we can bring in the same analysis we did on the last problem. So we still compute b times sine alpha and get 3.8567. This is the min length that a can be in order to make a triangle. So a is too short, and we say that this triangle is not solvable. So if a shrinks to a length of 3, then no value of beta will allow us to reach the horizontal segment. 3 is too short. Okay, and then the next page. Notice once again we have the same alpha and b. And this time our value of a is 5 feet. But because we have the same alpha and b, we can bring in our flow chart for determining the nature of solving this triangle. Notice that a is shorter than b, and it's longer than this perfect length that would allow me to create a right triangle. That puts a into this category, and we're going to have two triangles as possibilities. So this scenario is solvable, And let's go ahead and try to find both of the triangles. So let's grow A to 5 units long. So one triangle will be roughly in this position where beta is around 90 degrees, but another possibility will be this triangle where beta is around 10 degrees. Let's complete this version first. The angle opposite B we'll call beta, the other angle is theta, and the side opposite it is C. Let's use the law of sines with a B beta ratio and an A alpha ratio. We're trying to find beta, so I'll start off by saying the sine of beta divided by its opposite side B must be equal to the sine of alpha divided by its opposite A. Multiply by B, substitute values, and then do an arc sine. Now this argument will be positive, which means when I do the arc sine of a positive number, I get a first quadrant angle, or an acute angle. I'll use B equals to stand for beta, so I don't have to type out the word beta. Arc sine of 6 sine 40 over 5, make sure you are in degree mode, and we get about 50.47 degrees. Now we can find theta by doing 180 degrees minus alpha minus beta. I use capital T for theta, 180 minus alpha, which is 40, and then minus this beta, and I can just type in capital B, and we get about 89.53 degrees. And now we can find C using the law of sines. C divided by sine theta is equal to, and I'll use the A alpha ratio, A divided by sine alpha. C is equal to A sine theta divided by sine alpha. A is 5. I'll leave theta unsubstituted. I'm going to use technology to substitute the precise value of theta into this position, and then divide by sine 40 degrees. So C is equal to A, which is 5, times the sine of theta, using capital T for the theta, divided by sine 40 degrees, and we get about 7.78. This would be measured in feet. And this is our first option for a triangle, and it is an acute triangle because all of the interior angles are less than 90 degrees, although theta got close. Now let's find option 2, where we know beta is going to be around 10 degrees, and our triangle will look like this. So we still have an alpha of 40 degrees, B is still 6, A is still 5, but my beta will be a different beta this time, clearly an obtuse angle. Let's call it beta sub 2, and over here, let's call this one beta sub 1. Theta will be this acute angle up there, and C will be this short side over here. Now, how do I find beta 2? Because if I set up the law of sines and repeat this process, I'm still going to get beta equals about 50.47 degrees. In fact, the arc sine cannot give me a obtuse angle. If you recall, the range of arc sine is only the fourth or first quadrant, so I cannot get an angle between 90 and 180 degrees. But looking at this image, this triangle right here would be isosceles. This side and this side would be the same, both 5. Therefore, this angle and this angle would be the same, and they're both this value of beta I got, the acute angle. We call that beta 1. Well, focusing right here then, we know that beta 1 and beta 2 have to be supplemental. They must add to 180 degrees. So we can find our second option for beta, calling it beta 2, by doing 180 degrees minus beta 1. Well, in our programming over here, capital B stood for beta 1. So let's create a new line for B sub 2, or beta 2. And we get this supplemental angle is about 129.53 degrees. All right, we can now find theta in the same way that we did before. Theta is 180 degrees minus alpha minus this beta 2. Let's call this capital T sub 2 for theta sub 2. 180 degrees minus alpha, which was 40 degrees, minus beta sub 2. And we get about 10.47 degrees. Let's go ahead and call this theta 2. And therefore, over here, let's call all of those theta sub 1. And now let's find C. C will be much shorter this time than it was last time. Over here, all these values, let's call them C sub 1. And now let's find C sub 2. So we know C2 divided by the sine of theta 2 will be equal to A divided by sine alpha. Therefore, C2 is equal to A sine theta 2 divided by sine alpha, and we get approximately 1.41 measured in feet. And because beta sub 2 is an obtuse angle, this second option is an obtuse triangle. All right, and this concludes our lesson on the law of sines.